All right, guys, this is our last day of Chapter 9 notes. So we're in 9.10. My first video cut off with this last example, so I'm just going to pick up here. So I've been sort of alluding to being able to have a shortcut to build some series. So we kind of have to be careful when we're building a new series based off of something that we've memorized. So here are the four that you had to memorize: sine x, cosine x, e to the x, 1 over 1 minus x. And here are their intervals of convergence. Quick way is just they all converge for all real numbers except the geometric power series, which converges on the interval -1 to 1. So if I want to find the Taylor series for e to the 3x, as long as I'm centered at 0, I can simply build the series using this property that we talked about a day or two ago. Where'd it go? Oh, sorry, it's in 9.9. Using this guy, I said, hey, we're going to get to these later. Remember how we said, oh, if you just have like instead of f of x, you have f of kx, you can literally just plug the kx into your power function and see what you get. All right, so for us, sorry, I'm scrolling all over the place. So for us, as long as we're centered at 0, because all of these are Maclaurin and all of these are centered at 0, you can build. Shortcut, build the series. Okay, what am I talking about? Build the series. When I build this, I'm saying, well, this is really just an e to the u, right? So I'm starting off by saying, okay, I know a power series for e to the x centered at 0. That power series is e to the x. And sometimes it's good to write out the terms, right? So it's 1 plus x squared over 2 factorial, x cubed over 3 factorial. Maybe we'll throw in a general term, plus x to the n over n factorial. It goes on forever. Or if you just want to get right down to the power series, it's the power series from 0 to infinity of x to the n over n factorial. If this is e to the x, and I want to build a power series for e to the 3x, as long as I'm still centered at 0, if this had centered at 1, I'd have to go back to the old method of finding derivatives. But here, since I'm still centered at 0, it literally means plug in 3x for all of these x's. So this is still 1. This is now 3x. This is 3x, the quantity squared, over 2 factorial. You get the idea. 3x, the quantity cubed, over 3 factorial. How would that change the general term? It would become 3x, quantity raised to the n power, still over n factorial. And so the power series would be the sum from 0 to infinity of parentheses 3x to the n over n factorial. Now, when you write that out, you could simplify it further. So you could take it to like 3 to the n, x to the n. You could also just leave it like this, though. It doesn't matter. Okay, so for our next example, and I can still check the interval of convergence, right? So if I check the interval of convergence when I build the series, I can say, well, for e to the x, normal interval of convergence was -infinity to infinity. We haven't done any calculus, so the endpoints really shouldn't change on this. So this still converges for all x. But if you're not sure, you can do a ratio test and investigate. Find the Taylor series for f of x equals x times sine x. Again, centered at 0. If we were centered at pi over 3, I couldn't build the series because centered at pi over 3, I don't have any 0 terms. I'd have a term represented everywhere. We had that on our quiz. But start out with the sine x series that you do know, centered at 0. All the odd powers of x, right? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial We'll do one more. Minus x to the 7th over 7 factorial plus the general term would be negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And the general series, we just write the series itself, it's taking that general term and putting it in the summation. So negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So when we say x times sine x, and we're still centered at 0, it does just mean multiply an x through each term for sine x. So multiply this term by x, you get x squared. Multiply the next term by x, you get minus x to the 4th. Still over 3 factorial. Next one becomes x to the 6th. I'm just distributing an x through all these terms. Minus x to the 8th over 7 factorial. So how would that change the general term? When you multiply by x, you're multiplying by x to the 1st. So when you add those exponents together, it's x to the 2n plus 2. But the denominator is still an odd factorial, 2n plus 1 factorial. Now, it's good practice to make sure that whatever you write for this power series actually generates the terms that you're showing. It's kind of like, how do you check your work? So let me write this out. So I should double check and say, okay, if I plug in 0, negative 1 to the 0 is 1. That becomes x squared over 1 factorial. I get x squared. Check. I'm just going to do one more. When I plug in 1, I get negative 1 to the 1st, so negative x to the 2 plus 2, x to the 4th, over 2 plus 1 factorial. Yes. So the only time that things kind of get messed up is when you do something and that first term becomes 0 all of a sudden, or things get kind of knocked back. So if this didn't match up, I would usually just make a minor adjustment, like, oh, should I just have it so that the first term is not n equals 0, make it n equals 1, and then does everything work out? Or do I just need to make a slight adjustment to one of my expressions? But you always need to check that your series actually generates the terms. Sometimes they will give you the terms and then you're writing the nth term for it. As long as whatever you write generates out to what they showed, you will get the credit, assuming you didn't do something crazy and write like an extreme case that would take forever to figure out. All right, so you'll see a couple of, I think you'll see one example in the homework where I had to make a slight adjustment. So that'll be on tonight's homework. All right, that's it for the notes.